All right, let's talk about buffers. And so buffers are a solution of significant amounts of both the conjugate weak acid and its conjugate weak base in solution that resists changes in pH. It is a special case of the common ion principle, which is just Le Chatelier's principle in action. So, a buffer which contains a weak acid and its conjugate base in solution, right? That's your definition. I got a conjugate weak acid, conjugate weak base. So, for example, here are some pairs of things that can make buffers. So, acetic acid and acetate, hydrofluoric acid and fluoride, ammonia, ammonium, phosphate buffer. The calculation of a pH of a buffer is just a common ion problem. And we saw common ion problems were pretty easy to handle, right? You just needed to do an equilibrium table that had both of the things in there to start. And so if I've got a buffer, the point of having a buffer is that it is able to resist these changes. So if I've got something like this acetate buffer, well, this is my buffer system. It's got my weak acid, conjugate weak acid, my conjugate weak base. All right, I've got an acid reaction that can happen. All right, so the acid reaction is that my weak acid will form H plus in the conjugate weak base. The opposite happens for the conjugate base, where it's going to form the conjugate weak acid and OH minus. So if I add OH minus to the buffer, what's going to happen is it's going to consume some of the, or neutralize some of the weak acid. Right, these two guys react, and I'll form water and the conjugate base. Well, the conjugate base, because it's in equilibrium with the conjugate weak acid as a common ion problem, right? It's going to resist that change. Right? Same thing that's going to happen with adding H3O. Well, if I add H3O to this buffer, I'm adding some of this. Not only am I adding some of this, I'm trying to make some of this. Right? So I'm going to take away some of this guy to form this guy back. So that's really going to shift the equilibrium. It's going to Le Chatelier says we're going to resist that. So I've got my acetate reacting with my acid, right? My conjugate weak base reacting with my strong acid, and it's going to form water in the conjugate weak acid again. So let's look at the following equilibrium, right? Where we've got our acetic acid forming the acetate and H3 plus. If our common ion is added, so our acetate over here, a conjugate weak base, say from adding sodium acetate, and then the concentration of the acetate increases, and the system is not at equilibrium anymore. Q is in at K, and it's going to shift back towards the reactants again. So the H3O plus concentration is going to have to decrease. My pH goes up. For our buffers, which are a mixture of the weak acids and the weak bases, I can look at this from the acid's point of view, right, where I've got HX, right, so, or HA, goes to H plus in the conjugate weak base. Our K expression would be that we'd have the H plus and the conjugate base over the conjugate acid, and so our H plus ion concentration is going to be about equal to Ka times the ratio of the conjugate weak acid to the conjugate weak base. Right? So if I add a little bit of H plus and shift one of these a little bit, right, it's not going to change the overall pH very much. Right? So when OH minus is added to the buffer, the OH reacts with the HX to produce X minus in water. But the ratio remains more or less constant, so it's not significantly changed. If I add H plus to the buffer, the X minus, the conjugate base, is consumed to produce HX, but again, it's a small amount, and the ratio is relatively constant, so the pH doesn't change a lot. Right. We've got this term called buffer capacity, and buffer capacity just means how much of the strong acid or strong base can be neutralized before there's a significant change in the pH. If I add some acid, the pH to the buffer is going to drop a little bit. If I add some strong base, the pH of the buffer is going to increase a little bit, but not a lot. You're going to keep within plus or minus like half a pH unit most of the time. Right? It's when you break the buffer and you go beyond the buffer capacity, then you'll see a large swing in pH. So like a little bit, right? Just a little bit. It's like the straw that broke the camel's back. Just a little bit extra, and you're going to see a huge couple of, 2 or 3 pH units change in the pH when you add that strong base or the strong acid in. And once you've broken it, the buffer capacity depends on the composition of the buffer. So how many moles of the conjugate acid do you have? How many moles of the conjugate base do you have? The greater the amounts of conjugate acid-base pair, the greater the buffer capacity. The exact pH of the buffer is going to depend on Ka, so that's going to set roughly where the buffer is. And then you can adjust it a little bit by changing the ratio of the conjugate acid to the conjugate base. Okay. If Ka is small, equal or less than 10 to the minus 3, then the pH of the solution containing a conjugate weak acid, weak base pair can be estimated by the following equation, which is called the Henderson-Hasselbalch equation. Right, so we had this. This was our just K expression rearranged to put H plus on the other side. Right, so Ka was equal to products over reactants. We're going to move this guy to the other side. Well, if I've got H plus on this side, I can take the log of this, and then I can take the log of these guys. So I can take the log of both sides. I guess Henderson took the log of the left-hand side, and Hasselbalch did the log of the right-hand side. I don't know. I'm just making that part up. But I end up with pH equals pKa plus the log of the conjugate base over the conjugate acid concentration, or the log of AHA if we're using A's and HA's. Right? So this is a thing that would be worth memorizing, but I would give it to you on a test. I don't think they would give it to you on your final, though. And you can see where this is where the pKa comes in useful. Right? So the Ka gets converted into a pKa, and if I've got equal amounts of acid form and base form here, right, my pH is going to be equal to pKa. So that's kind of the center point, is the pKa. All right. We're going to break our calculation for a buffer into 2 parts. We're going to calculate the amount of strong acid or strong base added. That results in a neutralization reaction where X minus is the weak base and HX is the weak acid. So X minus plus H3O plus is going to give me the conjugate acid and water. And if I take my conjugate weak acid and I add some strong base to it, I'll end up with a conjugate base and water. By knowing how much acid, strong acid, or how much strong base were added stoichiometrically, we know how much of the conjugate weak acid and conjugate weak base is formed or left in solution. And here's a little flow chart for that. Right, so you've got a buffer containing my strong or weak acid and weak base. If I add the strong acid, I do a neutralization step using stoichiometry. I recalculate the new concentrations of conjugate weak acid and conjugate weak base. Use Henderson-Hasselbalch to find the pH. Right? And the same thing happens if I do a base, except now I'm going to consume some of my weak acid to form the conjugate weak base, recalculate the concentrations, and then use Henderson-Hasselbalch again to find the pH. And I've got an easier way to do this. And just hang on for that. And this is the right way to do it, right? We're going to calculate the new concentrations, look at the number of moles, divide by the volume, get the actual concentration. That's the right way to do it. It's not the most efficient way. Right? So with the new concentrations, we just plug it back into the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of AHA. Now, there is another version of the Henderson-Hasselbalch equation, and they go through it in your book, and they call this one making an acidic buffer, and they call the other one making a basic buffer. They have slightly different forms, but they're still going to give you the pH, right? If I am making a buffer, and that buffer happens to be a basic buffer, I am not going to use the base form of the Henderson-Hasselbalch equation. I'm just going to use the regular acid form and convert my Kb to a Ka. That way I only have to memorize one thing rather than having to memorize the base form of the Henderson-Hasselbalch equation. It's in there. I've got it at the end of this lecture slide set. It's in the extra stuff, right? But there's no reason to memorize two things, and one thing will do if you just can convert a Kb to a Ka. Yep. So let's do one. Here, calculate the pH of a buffer solution. That's 0.1 molar in acetic acid and 0.1 molar in sodium acetate. Well, set up my balanced chemical equation. Ha plus water gives me H plus and A minus. I start off with a little bit of each of these. Right, 0.1 molar for the acid and 0.1 molar for the conjugate base. Lose a little bit of the conjugate acid, form some hydronium, form some conjugate base. Figure out what the equilibrium concentrations are. 0.1 minus X, X, and 0.1 plus X. Substitute that into my equilibrium expression with Ka. All right, so I've got X times 0.1 plus X and 0.1 minus X. X is small. Makes my math a lot easier. X is going to be equal to K. So if I want the pH, right, I'm going to take the minus base 10 log of my hydrogen ion concentration, which was X, right, 4.74. Okay, so there's the Henderson-Hasselbalch equation. That's the other easier way to do it. Right? I could have done pH plus pKa using the log of aha. See, he's surprised. That's how you remember it. It's ah over ha. And it just lets us do it for a buffer. Now, do not, just because you have this in your toolkit, do not assume every acid-base neutralization problem is a buffer problem. There are lots of buffer problems out there, but a buffer problem is only when you've got significant amounts of conjugate acid and significant amounts of that conjugate base in solution at the same time. Right? If I'm just doing like hydrochloric acid and sodium hydroxide, don't use Henderson-Hasselbalch. Right? So you got to figure out, is Henderson-Hasselbalch appropriate to use? If I've got a weak acid, like acetic acid, and I add in a lot of sodium hydroxide, is it Henderson-Hasselbalch? No, because I've got excess hydroxide. Right? So make sure you are in the right zone to be able to use Henderson-Hasselbalch. Okay? It is only when that X is small approximation is valid. So not only do I have to have both things in solution, but X also has to be equal, also has to be very, very small. So if I've got just a tiny, tiny bit of the conjugate base, not going to work. Tiny little bit of the conjugate acid, not going to work. I've got to have significant amounts of both of them. Okay, let's do an example. Using Henderson-Hasselbalch, determine the pH of a solution prepared by mixing 40 milliliters of a 0.5 molar sodium acetate solution and 60 milliliters of 0.5 molar acetic acid. Okay, pause, come back. It's A. All right, so pH is going to be pKa, so it's going to be around 4.75. I've got a little bit more of my acid, right, they're the same concentrations, but I've got 40 milliliters of the base, 60 milliliters of the acid, so the ratio is going to be 4 to 6. Right, so the pH is going to be a little bit lower than this. Right, double check, solve for the actual number of moles of base and moles of acid, put them in there, do the Henderson-Hasselbalch, and you end up with 4.57. All right, let's do another one. We calculate the pH of a buffer that's 0.05 molar pyruvic acid and 0.045 molar of sodium pyruvate, with the Ka of pyruvic acid being 4.1 times 10 to the minus 3. Pause. Come back. All right, good. The answer is 2.4. Right, I need to take the pKa of this. Right, it's going to minus base 10 log. This is going to give me the pKa. Here is my conjugate acid. And this is my conjugate base. So when it comes to the log of the ratio, this guy is going to be the one on bottom. That's going to be the one on top. Right, so when can I use ICE, the full equilibrium analysis, or the Henderson-Hasselbalch equation? Right? Henderson-Hasselbalch is only good when X is small. Generally, X is small will work when both of the following are true. Ka is small, and the initial concentrations of the acid and the salt are not very dilute. In other words, these concentrations are big. So, got to have big concentrations of both the acid and the conjugate acid and the conjugate base, and Ka has to be small. Right? Use HH only with a buffer. Right? Do not use it for any and all neutralization reactions. Double check to make sure it's both concentrations of acid and the base